Okay, and next up we have Jessica LibbyRoberts from Penn State, who will be talking about a spot of trouble. It's an adorable name.
Hi everyone, I am Jessica LibbyRoberts. I'm a postdoc at Penn State, and today I want to give an overview of some of the recent ground-based efforts we've been doing to monitor TOI 3A84 over the past few years, both in high resolution all the way down to photometry. I do want to note that this is going to be showing our results with a lot of questions, not answers. I realized in the abstract I had written that I would basically solve all problems of this mid-M dwarf. I was very naive, so bear with me on that. I also want to thank my many collaborators who are giving me the opportunity to present some of their work here today. Okay, so TOI 3A84, for those of you who do not know about this system, this was a very unusual system that we discovered. It really came about when we started folding test transits. We saw a peculiar bump in every single test transit, and it was the same bump in the same location across every single transit. Now, normally this bump, you would assume that it's a star spot crossing event, but how do you get a star spot crossing event that occurs at the same point every single time? And so this was a bit confusing, and the other thing we were a little confused about is we see no photometric variability on this star. So if it is a spot crossing, that spot is not rotating in and out of our view. So we were pretty worried that maybe this was contamination from like a nearby stellar companion. So we wanted to go and get data from the ground. So we could isolate this one star, and what we see is a star spot crossing event in every single transit from the ground. So nothing has changed, and in fact, this has been going on for like multiple years that we are seeing the same spot. And it really came about, I think, when we were able to get a really nice high-precision photometric observation with the 3.5 meter telescope at Apache Point Observatory. And what we realized when we were doing some spot modeling is that what we are looking at is a pole spot crossing event. So you have a spot on the pole, the star is aligned towards your line of sight, so it's rotating this way, so you never have spots coming in and out of view. And what's happening is this planet is crossing every time it crosses the exact same pole spot. And so from this, we were able to derive that this planet had a radius roughly around 6 Earth radii. And then we also followed it up with radial velocities with the Habitable Zone Planet Finder, a near-infrared high-resolution spectrograph. And we placed a measurement on the mass at 32 Earth masses. So this is actually what I would say a super Neptune around a mid-M dwarf, which already made this planet very rare, and even the alignment makes it even rarer. But we also used SpecMatch to derive stellar temperatures. We found the effective temperature to be about 3,200 Kelvin, which puts it at a mid-M dwarf, somewhere around like an M4 dwarf. We also found that it had a V sin I of about 3.5 kilometers per second. So this indicated that, yes, we were on the right path because that we are looking down the pole. Otherwise, we would have seen stellar variability because the star's rotation period has to be less than 4 days. So based on these measurements, also we got the metallicity and the log G. We published these values for the stellar mass and the stellar radius of 0.3. And I realized when you look at those error bars, I'm very embarrassed that I published those uncertainties. They're probably underestimated. But overall, this is a mid-M dwarf. So TOI 3A84b is the largest transiting planet that we have found around these types of M dwarfs. We also put an age of about less than 1 billion years, simply just from rotation, since this star does rotate relatively quickly. But what I want to indicate was, one thing we didn't show in our paper was we actually observed a RV during transit, and we had to remove that point because it just didn't fit very well in our RV curve. And in fact, when we took a closer look, one of the benefits of HPF is it covers the helium triplet that you would expect to see. And so when we looked at that point in transit, we saw a notable helium absorption feature coming from this transit. And so we went back and we observed 5 transits. And what I'm showing here, what I want you to focus on is the black line, which is the average of all 5 transits. And the blue lines are where you would expect to see helium absorption. And so there was a very clear indication of helium absorption. But the problem when you have an active star is that we don't know if it's coming from the planet or if the planet is crossing, say, helium emission on the star itself. And so the next step was to look at the out-of-transit helium. And so what we did was, what I'm showing is the transit depth is a function of time, and if you're unfamiliar with HET, it's on a track. So it basically stares at one area of the sky, and then the star sort of just passes over that track. And so we can't observe continuously. We had to observe multiple days, and what we saw was a nice helium tail. So to give you some numbers here, this is about a 0% transit depth, so no absorption whatsoever. We see a 5-hour pre-transit helium tail. This is one of the larger helium tails we've seen. And so that was sort of what clinched it for us, that this is actually coming from the planet itself. We also saw that the average transit depth is about 9% in helium versus an optical depth, which is about half that. So this is a massive helium exosphere that's being lost, and it's being lost pre-transit, but we don't see anything post-transit, which is a little bit unusual. And I was hoping to spend a lot of time actually showing you all the 3D modeling that we are doing, but we are actually having a quote-unquote fun time of modeling the helium escape. This planet's quite interesting. It's right on the limit of the Alpine radius, so there's likely to be some magnetic fields. So there is a big discussion right now that we are having of how is the planet losing this helium. Is it through Roche lobe overflow, which we don't think, or are there magnetic field interactions that are helping fuel this mass loss? But one of the benefits with with high resolution is we also probed a tentative RM signal, which I realize is ugly, but it basically is flat. And so when we looked at this, what we got was, we put a prior on V sin I at 3.5 kilometers per second, and we get a lambda, so an obliquity measurement between the star and the planet of about minus 80 degrees. And this is actually really promising because from our star spot modeling that we did, we actually predicted an obliquity of around 75 plus or minus 10. So we are like right on if we can trust these RMs. And again, this is still some work in progress, but it was an added bonus. Okay, but here's the issue. So I've talked a lot about the planet, but again, this is know thy star, know thy planet. And it turns out we are hitting some more snags. So what I'm showing here is not TOI 3A84. This is actually a different star, an similar M dwarf that we have from JWST. And we were actually able to retrieve the average photosphere temperature, spot temperature, and coverage fraction through JWST low resolution spectra. And this looks great, except one thing we noticed was the derived effective temperature is actually 200 Kelvin cooler than the photosphere temperature, simply because effective temperature is a combination of your spots and your photosphere temperature. And so we use effective temperature to derive so many stellar parameters, but if we are not correctly inferring that because of spot coverage fractions, this is a problem. And so the question now becomes, what happens when you have TOI 3A84, which has a spot coverage fraction of like 40% when you look at the effective temperature? So we had this idea that maybe we could try to look at a different bandpass and try to derive the contrast of the spot and therefore get a spot temperature. But we weren't able to do this. So the red line is if we assume that model that I showed previously and we just scaled it to the expected value, assuming an R-band measurement, it doesn't match. In fact, we had to completely remodel all of the spots, which I'm showing here on the right. And we also have a very lovely pre-transit flare that was going on that likely also impacted some of their spot modeling. So this was a problem. So we decided to go back, and we don't have multiband, we're not able to do multiband spectroscopy, or broadband photometry. So instead we did filter swapping, where we take one image in I, and we take one image in a different filter, and we swap back and forth and take images. Because our idea was, well, maybe if we just tried to model the individual I-band transits and then compare them to the whatever corresponded that night in either in G or Z, we would actually be able to derive a spot temperature from that. Unfortunately, what we noticed was none of these spot observations matched. If you kind of squint, that black line is actually our 2022 spot model. And you can see huge variations that we are actually observing in our spot model. And this enabled us to look at our transit. So we just compared the I-band transits that we are seeing. And you can see each of the black points are from 2022, and each of those colors are about a month apart. And you see incredible spot evolution on timescales of less than a month on this star. And so if you work on 3A84b, I want to point out that because of this, you have to model every single transit separately, because the spots are actually evolving from transit to transit. And I want to show some JWST data really quick. We did observe 2 transits. This is in December with NEARES, and 2 transits with NearSpec. I'm only going to show one of them because the light curves we've looked at, the white light curves, and they are they're something. But again, we see with 2 transits with NEARES, we see a flare pre-transit, and then we also see the spot as well. We don't see that flare in NearSpec, which was observed 4 days later. But the key point that I want to show here is that if you compare the 2 NEARES light curves, you can see this is 9 days apart. You can see clear variations in the spot in blue and green. And also in NearSpec, not as prominent, but you can see 9 days apart, very clear discrepancies in the spot as well. So we are currently working to model this to try to get a better understanding of exactly how the spot is changing over time. So with that, I will leave up my conclusions and take questions.
Excellent talk. We'll start right here in the front.
Thank you, great talk. Do the TESS transits also show variations, especially if it was observed in, let's say, the primary mission and then again in the extended mission?
So the problem with TESS is that the signal to noise is not great to try to distinguish like individual transits. We do notice that when we actually stack the transits and then look at in the bump and out of bump scatter, that the bump shows more scatter when you stack compared to the out of transit part, which does suggest that there is some type of change, but modeling it is really hard just from the signal to noise.
Is it a high cadence target in the extended mission or extended mission 2?
I believe so, yes.
Okay, cool.
Yeah.
That might be interesting to look at.
Hi, Sabina Saginbayeva from Stony Brook. So this is a star, also awesome talk. So this is a star I'm also spot modeling, and I'm following your paper a lot. But I wanted to ask if you see if the spot crossings in all of the transits are the same or actually more different maybe with JWST data, because I'm curious if this polar spot is actually axisymmetric.
Yeah, so that is one thing. We also see that the small spot that's probably rotating around. We also see that in our photometry as well. It seems like that small spot comes in and out of the transit chord. So one of our ideas, and that's probably what's happening with JWST, so one of our ideas is to try to track that to see if we don't have a stellar rotation. So to track that spot as it rotates around and see if we can actually pull out a stellar rotation from that, which then gives us a tight constraint on the inclination. Yeah, that's good.
Do you have any questions online? No? Okay, let's go to the floor.
That was really cool. I was curious, do you know if Arctic can support fast filter switching? And in the NEARES data, do you see anything cool in the helium pixel?
So the fast filter switching was what we tried with Arctic. And so it's about a 10-second difference between the two, as long as you put the filters together. So it can do it. But as for helium in NIRIS, we still need to take a look at that. We haven't. One of the issues is that if this tail is actually 5 hours, the NIRIS baseline starts like 2 hours or so. So we will already be in tail, if that makes sense, in the tail when we look. But we are going to look. And I think Katrina will be presenting more on that later.
Thank you.
Okay, we better wrap it up there, unfortunately, but let's thank Jessica again.